So now let's go back to the Bernoulli's formula for the binomial distribution, and there it is. Now, we don't care anymore because we've got the computer. The computer will handle this, and people have studied how to calculate this very accurately. But in the old days, all these calculations had to be done by hand. And as a result, there were lots of errors, and it was very difficult to do, especially when you're talking about n combination x. This number can be very, very big. If x is big, n is big, this number can be very big. Now, if x is big, this number here is going to be tiny, tiny, tiny. Well, either that one or this one will be tiny, tiny, tiny. So you're multiplying huge numbers, little numbers, multiplying all the accuracy. It leaves something to be desired if you're going to be doing all this by hand, including all the errors you're going to make just because you feel tired and you haven't had your cup of coffee, etc., etc., etc. So what can we do about this? And here is as big as we can make the quincunx. Okay, 19. What happens when n is large? Here's the quincunx, and now we're going to run it with n equals 19, and it looks lovely because we see all these little balls plop, 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 plopping down, etc. Now, at the bottom, we're trying to fill up 20 bins. It's going to take a long time, even if we run it at a very high speed. So I'm not going to bore you with this. What I'm going to do is I'm going to go to the results of having run it at 2002 times. You can see I tried to get 2000 exactly, so I wasn't quite as accurate. But look at the shape of how the bins have filled up at the bottom. It's a lovely, lovely shape. And if you do this repeatedly, try it for yourself. Just have a little patience. Let n run for a while. Choose a big one like 19, and then let it run for a while. I did it here for 2000. It'll take you a little while. You will find that every time you'll get this lovely shape at the bottom. This is the magic of mathematics, the magic of statistics. And this is what DEMOIVRE discovered. That if we look at this function here, if we look at this distribution, the binomial distribution, and if we make n very large, then the distribution is approximately normal. What do I mean by that? I mean that I'm going to always get this kind of shape down here. More properly, what this means is that if I standardize the variable, namely subtract the mean, which for the binomial is np, divide by the standard deviation, which is square root of np, 1 minus p. If I create the standardized variable, then this variable is approximately normal. What does that mean? It means that it will always have this shape. There is the mathematical expression. So not only will it have this shape, but this is actually the distribution of a continuous random variable. Remember, that was the apex of our taxonomy of variables in statistics. And what DEMOIVRE showed, brilliant mathematician, what he showed was that mathematically this magic happens. Namely, well, he didn't have a quincunx, but the bins in the quincunx would fill up to have this shape. A fantastic result. It's really the first, we'll come back to this when we talk about the central limit theorem. This is the first example of such. Now, of course, because we always foul up in naming things, this is sometimes called the normal distribution, or it's called the Gaussian distribution, named after a fellow Gauss who came maybe 100 years later and rediscovered this. Actually, he investigated it as the law of errors, but it's also called the bell-shaped, sort of more neutral bell-shaped. I guess bells look like this. Or the normal distribution, because at one time we thought that everything would have this distribution, therefore it's normal. But anyway, there it is. The normal distribution we see has two parameters, mu and sigma squared. So we're back to summarizing everything, just as we did in our empirical rule, by looking at the mean and the standard deviation. Now we get the entire distribution of the entire population by specifying just those two parameters. It's an idealization. It's wonderful. It's great. But there it is.